Breaking news, scholars have published the first ever archaeological survey of a comet. The results of this cosmic archaeology will surprise you. Stay tuned. Okay, we are here for our final segment of today. All that is old is new, and we're going to be delving into this really cool article that just came out earlier this week by my friend Justin Holcomb. We worked together in the lab in Greece together. He's now based in Kansas, and he published on the planetary geoarchaeology of comets, site formation processes on comets 67P Churyumov-Gerasimenko, or 67P C-G. And so in 2004, actually, this story starts with the Rosetta mission to this comet. It didn't get there until 2014. And then what they found archaeologically is really cool. Let's look into this. First of all, let's hear about this mission that was made.
This is the moment we made history by landing on a comet. 10 years ago, our Rosetta mission got up close and personal with a comet, landing a probe called Philae on the surface to directly study the properties of a comet for the first time ever. The mission was groundbreaking. It was only the 7th celestial object we have landed on before. It was an ambitious journey filled with many ups and downs, but we're getting ahead of ourselves. Let's take a look back at the mission 10 years on. Comets are large objects made of dust and ice that have elliptical orbits around the Sun, which stretch far out into the outer edges of the solar system. They are believed to be left over from when the planets formed, and scientists think they could hold the answers to how life formed on Earth, why we have water on Earth, and how the solar system evolved.
So this was a totally cool mission. It took 10 years from 2004 to 2014 for them to get there with this Rosetta ship, let's say, and then the lander, which was called Philae, and it landed on the comet. And it was able to do all these studies and tests that they wanted to and transmit it back. Rosetta actually orbited the comet for a couple years until it eventually lost power and crashed into the comet itself. So what this presented was the opportunity with all this data for the very first archaeological study of a comet, an in-depth archaeological study. And that's what was just published here by Luca Forasiepi and Justin Holcomb. Like I said, I know Justin quite well. He's a good friend of mine. So let's sit down with Justin and hear what he has to say about this.
I think that we're in this unique time. I actually think that we're in the middle of a transition, a space age transition from an early space interest in spacefaring to a solar system exploring species. Now, it could be 20, 50, 100 years, but historically, we'll look at this as our first kind of our forays. And we know when we look at initial dispersals, we have these initial forays, right? Pre-Clovis, Paleolithic Greece, right? Like this is no different.
So I don't know, how would you define this discipline of space archaeology, or I mean, you could planetary geoarchaeology, but let's start with space archaeology.
Yeah, I think space archaeology is really interested in our kind of what you could call a material footprint of space exploration and all that entails. So it's pretty broad. So it's the material record of, our existence in the solar system. And that could include in orbit and interplanetary space, dwarf planets, asteroids, comets. But also space archaeology does include, I said out of atmosphere, but it does include stuff on Earth as well. It includes anything related to the kind of space exploration. So launch sites, crash sites as well, but also like observatories. It's kind of inextricably linked to the history of rocket science. People actually even looking at the cultural heritage of Arctic explorers, right, as an analogy to space exploration. I would say it started really in the early 2000s with Pete Capillotti. Yeah, he's did the book on the moon, and he's a really great guy. Moved the field forward for thinking about Apollo objects and the first boot prints and things like that. And Beth O'Leary working with Lisa Westwood, really focused on kind of launch sites and crash sites as cultural heritage. And so the idea of solar system as a cultural landscape is like, that's the first epiphany, really, for me, kind of changed my thinking. I realized, well, what about the stuff that's on the surfaces of celestial bodies? What's happening to it? And, as a geoarchaeologist, it was, a geoarchaeological problem. Like,
Hmm.
what are the processes, both cultural and natural, that may be affecting the stuff that is on these different celestial bodies? And so that's what planetary geoarchaeology is. It's a form of space archaeology, but it's just on the actual material on these other celestial bodies.
I'm thinking about this from a geological point of view. So, geology, you're studying kind of sedimentary processes, what happens with dirt erosion or
Right,
fill or
right.
damage due to earthquakes or other kind of natural phenomena. And so you're trying to look at these in areas of landing sites or impacts or whatever and model, I suppose,
Yeah.
what's going to happen in the future in those specific localities.
Right. I always talk about it kind of in like turning points of my thinking. So if the first turning point was that space archaeology is a thing, which it was, trash on the moon and there's a galactic litter, and it just dawned on me, I was like, wait, this stuff isn't trash, right? Like, why are we talking about it like it's trash? Like this stuff
I
first.
mean, that's what archaeologists study is trash,
Right.
after all,
Yeah.
right?
Right. It's more than trash, I should say. It's certainly
Yeah,
trash, but it's more than trash. For me, I'm a Karl Popper guy. I Popperian, all science begins with problems. And if you coin a space trash problem, that means you must have a solution. And the solution is preservation. We need to actually preserve a lot of this stuff.
No, I think that makes a lot of sense, and I think it's important to try to bring this archaeological voice to these archaeological sites, these remains
Yeah.
in many ways. Have you convinced some to see it as heritage rather than just trash?
When I first got into it, I thought I was going to have a lot of, I don't know about pushback, but maybe just be like ignored by the planetary scientists. And then like the archaeologists would be like, yeah, but you know what? It's been the opposite. Like
Cool.
the planetary scientists are like all about it, but the archaeologists are kind of, other than you, I guess, are kind of like, I don't know. Is it archaeology? Like I've had some people say, well, it's too modern to be archaeology. It's not archaeology. It's not old enough or, you know, and
Yeah, but it's
obviously
applying
I disagree.
archaeological methods. I completely disagree. I mean,
I agree. I
you
disagree as
you can
well. Yeah.
study the archaeology of yesterday, and
Yeah,
that's
exactly.
valuable in its own way. We actually do that all the time. We call it ethnoarchaeology
Right.
oftentimes,
Yep.
but we study the archaeology of yesterday all the friggin' time.
Oh, yeah.
And so,
And contemporary archaeology is a thing, right? Like,
yeah.
if you're still thinking that stuff has to be old to be archaeology, you're probably not, I don't know, well read, I guess. Not to sound mean, but like,
Yeah, so you
yeah,
just published this paper on the geoarchaeology of this comet 67P.
yeah,
And so, yeah, walk us through what your goals are with this paper.
right. So the solar system is a depositional environment.
Hmm.
So, as geoarchaeologists, when we are looking for archaeology sites and we find artifacts, the first thing we say is, what type of environment was this artifact left behind in? Is it an environment dominated by wind, like an aeolian environment? Is it an environment dominated by water, an alluvial environment, gravity, a colluvial environment, right? Hill slopes. And then I realized that, oh, there's like another missing chapter to that geoarchaeology text, which is comets and asteroids, moons. Those are all typically airless bodies, not always, but typically airless bodies, planets and dwarf planets, orbit, and interplanetary space. And in each of those, we need to actually figure out what are the processes operating in those environments to deposit materials that might bury archaeology sites, aka archaeological formation processes. So that brings us to comets. The first idea there was, okay, well, let's talk about one. Let's pick a case study to talk about a celestial body as a depositional environment and how it may be affecting cultural material. We started with the moon. The moon has a lunar premise in the sense that people think that whatever's on the moon just preserves forever, right? But what's happening on the moon? How dynamic is the moon? And in the end, it's like the perfect case study. And some of the reviewers said that. They're like, yeah, we like this idea, but it's the perfect case study. Enter comets. Comets is like the worst case study, like other than the sun or like a gas giant.
It's a harsh environment. It's
Yeah,
frozen and then it's
yeah,
hot and then
but
yeah.
it's still going to preserve But the question then was, how long will things preserve on comets? I'll talk about it a little bit, but I don't want to go into too much of it because it's actually my co-author, Luca Forasiepi's research. So Luca is space archaeologist, and he's actually the very first master's thesis that did a planetary geoarchaeology master's thesis. So we co-authored, and I helped him kind of wrap his idea into a geoarchaeological bow, basically. We've researched about 8 different comets. 2 of those we've interacted with. And 67P we actually landed on and then also crashed into. So there was, pretty arguable preserved archaeological record on 67P GC. The idea was is how long is that material going to be there? Can we go and sample it? You mentioned about this idea of modeling. That is a form, that's like the main way we could do planetary geoarchaeology today. I call it predictive analysis. The second one is like active primary analysis, which is sampling and bringing it back. That's where I
Yeah.
want to see us get to. And so the idea though was how long, if we were going to do that, how long could we do that on a comet? And so we call it it's got a preservation window. And it's basically these comets are orbiting around the sun. So as they get closer to the sun, it gets more and more volatile. It loses more and more material through outgassing and jets coming out of it, gas jets. And so it can launch stuff out into space. And so
So you're
that was the
basically
idea.
saying comets fart when they get close to the
Yeah,
sun.
exactly. They do, yes. And so, they get gassy and um,
In a sense, what were you using to help model this? You were using actual video footage and descriptions and other things, photographs from the mission there in 2015, 2016?
the Rosetta mission in particular actually orbited the comet for a while, collecting data, collecting geological data, and tons of imagery, which actually allowed to see things moving. And so Luca, in consultation with ESA scientists, European Space Agency, they were able to at least make guesstimates. It's the best we can do with what we have. When I mentioned earlier about sampling, I think a lot of people are like, so what? We're going to spend billions to send archaeologists to space? No, that's not what I'm saying at all. I'm saying we add a single experiment to the long list of scientific experiments that astronauts already do. And we can consult and guide on how to do that. We sample sites. You've sampled Knossos and other sites on Crete,
Yeah, of course.
you know, and we have formal processes. You've got to have a permit. You have to have research questions and hypotheses. We already know how to do all that. So actually, at the overall, one of the big things I'm arguing is that we need cultural resource management in space.
Yeah, I think that makes sense. And I think it would be really cool to add that to that long list of different things. We're
Yeah,
already doing it with so many other disciplines, so
right.
many other sciences. And I think it would also go a long way towards getting, the public's already interested in both space and archaeology. So you bring
Yeah,
those two together and you have that perfect sort of
yeah,
interest that you can generate and
right.
demonstrate the relationship between these different sciences.
Exactly. And not
Yeah.
to mention, it's not just about this material being the recording our first footsteps. That is a big part of it. But as archaeologists, we know that when things are put in the ground, they're still recording data,
Yeah.
right? They're recording depositional and post-depositional processes. And so, and these are recording data on extraterrestrial environments, right? So Mars, they're getting, abraded. We can look at space weathering, radiation. We can look at wind action. Mars has a cryosphere. We can look at what the cryosphere does to certain materials. So, yeah, all of that, when you sample that material and bring it back, we can get really good geological information from it as well. It's not just about doing archaeology, it's geoarchaeology.
Yeah.
Some of these environments, man, the moon is oh man, it's so volatile. Like there's never been water on the moon. So all of the regolith, none of the sediment, the dirt is rounded. It's all angular,
Hmm.
dust, silt. And so it's also electronically charged from solar radiation. So it just jumps and sticks to you. And it's this super caustic, imagine breathing that in, right? Like,
Yeah, seriously.
yeah, so the moon's pretty harsh.
I think all these environments, I mean, reading about that comet and seeing some of the
Oh,
images
yeah,
and footage from there, that's pretty harsh. Some of that stuff to get people there would be, woof.
I
I wouldn't
know.
want to dig through that space dust.
Right. And Mars too. The moon and Mars have earthquakes or moonquakes and Marsquakes. So we normally study the geological environment anyways. And so all I'm doing is just taking what I would normally do and then looking at these different environments with completely different non-analogous kind of processes. And it's super fun to do that.
Well, this was very cool. And yeah, if you have any last things you want to say for the recording.
I would just say, um, what the main idea is that we know as a species, Homo sapiens, we left Africa around 180, maybe 200,000 years ago, something like that, maybe um, into Greece and around the world. And all I'm saying is that that migration, that dispersal has continued into space. And so the hand axe in East Africa recording our earliest ancestors, as Homo sapiens at least, is the same as the broken Curiosity helicopter, wing on Mars. I think those are inextricably linked through our history. And from that perspective, I do think it's important to raise discussions about our need to potentially protect some of this stuff. I'm not saying that we shouldn't be exploring space. We absolutely should. And I'm certainly not saying we shouldn't go to certain areas. We absolutely should. But we should come up with protocols to do it ethically. And we should talk about the need to protect some of these earliest sites, not just American either, Soviet sites as well. Chinese, India has their first lander on Mars. As you said, it's a humanitarian effort, and so for the first time, we could actually look at one of those events and then keep track of it and not try to figure it out later.
Yeah, I think that makes sense. I mean, if you think about Star Trek, those people in the future looking back to our time of early
Yeah.
space travel, having those
Yeah,
sites
exactly.
there is going to inform them a whole lot. And so we should think now about long-term preservation because we
Yes.
can understand that as archaeologists. We look back and we look forward with the same perspective. Yeah.
Yes. And we're always reactive. We're always solving problems after they happen. Let's not do that this time.
Yeah, that makes sense. And I
And
mean, so
so,
much of the field is moving towards what these things mean for us today anyway,
right,
and
right.
trying
We
to
kind of have to.
recognize
Well,
the role of the past in the present. And so, that's going to matter for space exploration as
yeah,
well as for other things. And I think, one of the big questions with space exploration is who has rights over stuff, and hopefully your efforts here will help everybody understand that this is world heritage, worldwide heritage,
right.
humanity-wide heritage, maybe is the right way to put it. So there we go. Big thank you to Dr. Justin Holcomb for coming on the channel and sharing some of his stuff. I have a plan for a future video that talks about more space archaeology in general. That's been a plan of mine for a while, and I've been setting it up with Alice Gorman, Dr. Space Junk, as she's known. So you can look forward to that in the future at some point. But I thought we'd dive in really quickly to some of the details from Justin's article because some of them are kind of cool, and I want to challenge you all to see this archaeology. So, what he does as a geoarchaeologist is he looks at what's called formation processes. In a sense, formation processes are all the natural as well as human processes that impact the archaeology that we find. So, like a human process is that trilobite we saw earlier in the episode, which was moved from its geological context to an archaeological context. Or, shoveling dirt to build a foundation. That's a human process. Erosion, on the other hand, would be a natural process. And so we can see they've not we they have put together the range of different formation processes on comets. A lot of them have to do with the temperatures. It's further away from the sun and closer to the sun. When it's further away, it's frozen. When it's closer, it starts heating up and getting quite hot, and that's where it gets all gassy and has those jets that we see behind it inside the sky when we see a comet flying, when it's visible, I should say. And that causes all kinds of things like pit formation, fracturing. It can eject stuff out. But then, of course, there's human activities like the impact of the Rosetta on the surface of the comet itself, or the same thing with the Philae vessel. And so there's all these kind of activities that impact these comets and these archaeological sites from human exploration on these comets themselves. So here we go. I'm going to give you guys a second. We have a photo here. We have a couple of these photos. So what are we seeing here? What is this? This is a photo of archaeology. This is archaeology on this comet 67P dash or slash C dash G. So this is one of the key archaeological sites here. What are we observing? I'm going to wait for some comments to come in. Give this a thought. It's conveniently circled for you. I didn't do the circling. This is from the publication. What are we looking at? And will this survive? How long will this survive? So Fiery Waco says human footprints. No, no humans actually came to the comet. So these are not human footprints. Maybe the emphasis on some of my syllables, the emphasis that I gave, it might help out here. Impact from spacecraft debris. They dug up samples. Meteorite impacts. These are some of the guesses that we have. So Regalius, these would not be meteorite impacts because this is archaeology. Meteorite impacts would be natural processes. This is anthropogenic right here. Impact of the satellite and footprints of the landing robot. Yeah, so some of this is closer. So when the Philae landed, if we go back a second, no. This is the artist's reconstruction of the Philae that landed to take samples and to communicate back with the Rosetta, which was orbiting the comet and then sending stuff back. When the Philae landed, it landed at 1 meter for every 10 seconds, I think it was. It was landing at quite a fast speed, and it bounced. It had to bounce at least twice before it ended up settling down. And so this is 2 of these, B and C, are the depressions of the legs from the lander. A over here is actually not a depression. It's the sediment that was kicked up when those legs hit. It accumulated here. And so that's more of like a little mound of sediment that came down. And so this is the impact from that kind of crash landing that the lander had. Okay, so we have one more image. What are we looking at here? What are we looking at here? This one's complicated. There's actually several things going on here, and I'll be intrigued if anyone gets this one right. This one is some really cool archaeology, by the way. The last one, okay, we have some impressions in the soil. Here we have some really interesting stuff going on, in my mind. So let's see. What do we see here? We have some arrows. We have some other things. Look at it closely. Nope, sorry. What do we have here? What are we looking at? This is an image taken by the Rosetta, which is orbiting the comet. So we have debris still in science probes. Okay. We have drag marks. We have a fallen over rover. We have the broken sample collector. The impacted remains of the satellite. I'm actually impressed. You guys did a pretty good job. So right here, this right here is the Philae, that probe. When it bounced twice, it did not make a good landing. It did not land well. This is the artistic reconstruction we saw earlier with it landed. No, it ended up landing on its side. So it actually was only able to work for 72 hours, I think, because of where it landed and the fact it landed on its side. It lost power. It ended up powering up again about a year later from the heat of the sediments near it. But yeah, it fell on its side. What the arrows are pointing at, do you see these kind of long lines here? These were from the legs of the probe. They were dug into the sediments here, in a sense, a groove that was dug in as this probe was kind of tumbling. Somebody said that, drag marks here. That's what these arrows are kind of pointing at, is these kind of, not drag marks, but impact marks from the long legs of the probe itself. So I got to say, you guys did an excellent job of reading this archaeology quite well. So in terms of what would survive and what would not, in case we came back to this comet to try to excavate and look at this heritage of early space exploration, these prints from the bouncing would not last. They're gone already, without a doubt, without a doubt. The probe itself is maybe, we'll look at that in a second, and we'll look at the craft, the Rosetta, which crashed into the comet after the mission was completed. So the probe, the Philae, it was in this area of the comet that the scientists called Abydos, and there was this overhang over it. That's why it ended up losing power, is because it was in the shade and it was solar powered, and it didn't get enough power to work for more than, say, 48 to 72 hours. But eventually, as this comet keeps rotating around the sun, when it gets close to the sun, it's going to heat up this overhang that it'll probably eventually collapse. And it'll collapse and it'll bury the Philae probe. And then it'll depend on what happens. If there's enough heat that it causes those gassy jets to happen, it's possible that this entire deposit and the probe itself might end up ejected out into outer space, in which case nothing will survive. On the other hand, if they get lucky and this ends up in an area that is not too heated up, it's possible that future archaeologists one day will be able to go and excavate this and find the Philae probe in order to understand our early space exploration from 2014, which would be really friggin' cool if we did that, right? Okay, what about the actual vessel itself, the Rosetta? It crash landed in. It orbited the comet for a few years, reporting and sending back stuff. I think it was for 2 years, 2014 to 2016. That sounds right to me. And then once the comet got too far away from the sun, it was losing power. So the scientists chose to crash land it into the comet. And so it landed in this area called Sais. And it's in this area without a ton of deposition. However, there is deposition that occurs seasonally. So during certain periods, there's this kind of falling of sediments that occurs. Let me find a video of this. There's a cool one on Wikipedia. This is from this mission. This is the windfall of material that falls on the comet. So this is some of the footage that was taken from this very comet. And this is the kind of windfall of material that will, during certain seasons, bury this vessel, the Rosetta, partially. However, once it gets hot, it'll, boom, start ejecting this stuff. And the only stuff that'll be left behind is the material that's heavy enough that it won't get ejected. But there's a good chance that the Rosetta itself will get ejected at some point, and most of this material will disappear because it won't have that protection of something covering it, and it will eventually, even those larger material will probably end up ejected out as the comet keeps reworking itself from heat and cold. Eventually, those processes are going to break everything down. And so Justin kind of estimated to me informally, maybe 7, 8, 10 years, something like that. So we're probably already too late to record this site 10 years later. So yeah, that's how long these would last. So with regards to space archaeology, I think it calls into question the whole name of this program. This is old news with Flint Dibble, but this was actually new news. It was news about space travel from just 10 years ago, right? So what is archaeology? We always hear about archaeology. Archaeos means old, logos means the study of. So the study of old things. This kind of space archaeology really challenges our perceptions of the field. And I think that that's really fascinating. We need to, the field of archaeology itself is slowly changing, and we're trying to apply these kind of archaeological perspectives and methods to new things. So it's not just the study of new things. It's about applying this kind of long-term perspective on material evidence, and we can apply that to the past, to the present, and to the future. And so we're going to change the title of this program from Old News with Flint Dibble to both Old and New News with Flint Dibble. No, I'm joking. We're going to keep it as Old News. But I do think it's important to challenge our own perceptions of these kind of things. And so that brings us to the end of Old News with Flint Dibble, episode number 2. Breaking news! Scholars have published the first ever archaeological survey of a comet. The results of this cosmic archaeology will surprise you. Stay tuned. A large genetic study has revealed the very first dogs to be introduced to South America. Let's look into the who, what, where, and why. Was alcohol a driver for the development of complex societies? A big data study from around the world looks at the causal relationship between alcohol and human civilization. Is the drunk hypothesis correct?
Yeah, probably. We found the support for it.
All this and more on Old News with Flint Dibble. I'm Flint Dibble, and I'll see you Sunday.